Synthesis and release of bilirubin. Each red blood cell contains approximately 270 million hemoglobin molecules. Red blood cell lifespan is around 120 days. 100 to 200 million red blood cells are destroyed every hour. The process of destruction of red blood cells occurs in the spleen. Approximately 6 grams of hemoglobin is broken down per day. Red blood cell lifespan is around 120 days. Old or damaged red blood cells are removed from the circulation by macrophages in the spleen and liver, and the hemoglobin they contain is broken down into heme and globin. The heme contains precious iron that is conserved and reused in the synthesis of new hemoglobin molecules. During its metabolism, heme is converted to unconjugated bilirubin. Heme is released from old red blood cells. In a smaller part from myoglobin, cytochromes, bone marrow cells. Macrophages absorb residual heme. Heme oxygenase degrades free heme into biliverdin. Biliverdin is further converted by biliverdin reductase into bilirubin. Note the similarity in the structure of heme and bilirubin. The bilirubin that was formed is toxic. This renders the molecule essentially insoluble in aqueous solutions at neutral pH, cannot be excreted from the body in this form. Bilirubin is released into the plasma and is taken up by albumin, which serves to transport this molecule to the liver. Handling of bilirubin by hepatocytes. Albumin-bound bilirubin enters the space of DISI and bilirubin is transported into the hepatocyte. In the hepatocyte, bilirubin is either mono or deconjugated with glucuronic acid. The so-called conjugated bilirubin is formed. Glucuronic acid has good water solubility, which makes bilirubin highly water-soluble. Conjugated bilirubin contains 2 glucuronic acid molecules if unconjugated bilirubin binds to 1 molecule of glucuronic acid. Conjugated bilirubin, monoglucuronide, is formed, if with 2, conjugated bilirubin, diglucuronide. In the liver, bilirubin is conjugated with glucuronic acid by the enzyme glucuronol transferase, first to bilirubin glucuronide and then to bilirubin diglucuronide, making it soluble in water. The conjugated version is the main form of bilirubin present in the direct bilirubin fraction. Much of it goes into the bile and thus out into the small intestine. Conjugated bilirubin is found in bile, which accumulates in the gallbladder. Bile enters the small intestine during food intake. Further, the next stage of the conversion of bilirubin begins in the large intestine. Urobilinogen is formed under the influence of bacterial enzymes beta-glucuronidases and glucuronic acid is separated. Note the similarity of the structure of bilirubin and urobilinogen. The structure is very similar, but the double bond is replaced by a single bond in the urobilinogen molecule. Most of the urobilinogen, about 90%, is converted to strechobilin. Stercobilin is excreted in the feces, giving stool its characteristic brown color. A smaller part of urobilinogen, about 10%, is reabsorbed in the intestine. Urobilinogen is delivered to the liver via the portal vein system. A small fraction, typically less than 5% of the urobilinogen pool, is lost to the urine on a daily basis, and is thought to contribute to urine's color. Unconjugated bilirubin, lipid-soluble. Conjugated bilirubin, water-soluble. Bile O produced in the liver. O it accumulates in the gallbladder. O secreted in the duodenum 12 after meals. O mainly water. O contains phospholipids, electrolytes. O it contains bile acids necessary for the absorption of lipids. O bilirubin, excreted from the body. Bilirubin metabolism. Clinical evaluation. Serum bilirubin. Total. Conjugated, direct. Unconjugated, indirect. Urine urobilinogen, normally a small amount. Bilirubin in urine, conjugated, normally absent. 4 common causes of increased bilirubin hemolysis. Biliary obstruction, cholestasis. Liver diseases. Special reasons. The level of indirect bilirubin increases with hemolysis, direct bilirubin, with obstruction. Both conjugated and unconjugated bilirubin increase, with liver disease. With an increase in the level of bilirubin, it is important to evaluate whether the increase in bilirubin is isolated, or there is an increase in levels and other indicators of liver function such as liver enzymes, alkaline phosphatase. Special causes should be ruled out if bilirubin is elevated in isolation. Allocate hepatocellular and cholestatic type of liver damage with an increase in liver enzymes and alkaline phosphatase. A further differential diagnosis should be made to clarify the cause of the liver dysfunction and appropriate therapy.